Exercise 10 of chapter 13 is focused on generalized eigendecomposition. This is an important mathematical framework because it is the backbone, the mathematical and mechanical backbone for a lot of analyses in machine learning, in particular linear discriminators. So anytime you have a discriminant analysis or classification analysis, if it is a linear classification method, multivariate method, it is likely to be based on generalized eigendecomposition. So this framework is used a lot in biomedical engineering, in multivariate data classification, and so on. Okay, so here we are exploring one particular property of generalized eigendecomposition. So when we think back to regular eigendecomposition on one matrix, if that matrix is symmetric, then you know that V transpose V, where V is the matrix that has eigenvectors in its columns, V transpose V will be the identity matrix, and that is because V is an orthogonal matrix. Okay, but then we have so that property doesn't hold immediately for a generalized eigendecomposition, even if both matrices A and B are symmetric. So if A and B are symmetric matrices, their individual eigenvectors matrices will be orthogonal, so V transpose V will be the identity matrix. But the generalized eigendecomposition on A and B is not going to have this property. And essentially that comes from the theory of generalized eigendecomposition, and that is because you can think of generalized eigendecomposition on two symmetric matrices A and B as a regular eigendecomposition on the matrix product B inverse times A. And B inverse and A are both individually symmetric, but the product of two symmetric matrices is not going to be symmetric, at least not in the general case. Obviously, there's always exceptions, right? If one of them is the identity matrix or the zeros matrix, there's always these little weird exceptions. But in general, the product of two symmetric matrices is not symmetric. Okay, and that is something that we have demonstrated several times before in this book. Okay, so it turns out that the eigenvectors of a generalized eigendecomposition are orthogonal, but they're not orthogonal with respect to each other. They're orthogonal in the space of B. So that means that for a generalized eigendecomposition, V transpose V is going to be some matrix product. It's whatever it is, but this is not going to be the identity matrix. But when we stick B in the middle, then we actually do get the identity matrix like this. So V is orthogonal in the space of B. And this is pretty interesting to think about because if you would basically substitute V for I, so imagine B is the identity matrix, then actually this would hold, right? Because then we just have the identity matrix implicitly in here. And if B is the identity matrix, then the generalized eigendecomposition works out to be a regular eigendecomposition with the other matrix being the identity matrix. Okay, so the goal of this exercise in code is basically to produce this figure which will illustrate this property of generalized eigendecomposition. Here is the code. I'm creating two random symmetric matrices. So the matrix A equals A transpose A, which is random number matrix times itself. Same thing for B. And here we implement the generalized eigendecomposition on matrix A and B. And I've mentioned earlier in this chapter, but if you're going to perform generalized eigendecomposition, it's better to use the eigh function from SciPy that is more numerically stable compared to the eig function in NumPy for the generalized eigendecomposition problem. Okay, so let's see. Then we have V transpose V. I guess I could have written it like this, but anyway, it's the V transpose times V, and here is the same thing, but with B in the middle, matrix B in the middle. And remember that when you take the generalized eigendecomposition like this, you input A and then B as the second input. B is acting like the denominator matrix, so to speak, in the generalized eigenvalue equation. So This is like the denominator matrix. It's the matrix that in theory gets inverted, although in practice, you don't actually literally invert this matrix, which is useful because it means that you can perform generalized eigendecomposition on a reduced rank matrix, which often happens in practical applications. Anyway, the rest of this exercise is pretty straightforward. So now we are just going to visualize these two matrices here. Okay, so just a little error message here because when I'm recording this, I did not run all the code from the rest of this book chapter where I imported this function. So I just ran that code to import the eigh function from scipy.linalg, and of course now this works. Okay, and now this figure over here on the right looks like the figure I showed in the book. This one doesn't, but that's because these are random matrices and there's no constraints on what V transpose V should look like. So each time I rerun this code, it's going to look different because it's just random numbers multiplying each other. Okay, the last thing I want to do is just print this out. VBV, which is actually V transpose B times V. And you can see that all of these numbers are really, really tiny. So this is just 0 plus rounding errors.